In many parts of the world, the rainfall is not uniformly distributed over time and space. Further, the amount of rainfall is not adequate to meet the water requirements of crops. To supplement this deficiency, irrigation is practiced. India has got 1/5 of the world's irrigated area, which contributes to make it potentially one of the richest agricultural countries in the world. Irrigation has been practiced in India from very early times through wells, tanks and small channels. But the increased demand for food production has resulted in development of various other irrigation schemes. These irrigation schemes mainly consist of storage or diversion structures and distribution systems. In this program, we will cover the distribution systems comprising of open channels. Natural drains that exist on the earth vary in size from tiny hillside rivulets, streams, small and large rivers, to tidal estuaries. The geometry of the natural channels is in general very irregular. But normally, these channels have plenty of water and have their own course. Hence, they do not provide water at the desired location and in required quantities. This has resulted in human intervention with the natural channels and the development of artificial channel networks. These channels are classified according to their method of construction, cross-sectional area and alignment. The canal is a long and mild slope channel which may be lined or unlined. The flume is a channel usually supported on or above the surface of the ground to carry water across a depression. A channel having a steep slope is called a chute. If the drop in elevation occurs in a short distance, the chute is then called a drop. A covered channel flowing partly full to drain water across the highway and railroad embankments is called a culvert. It could be rectangular or circular. You might have noticed by now that these artificial channels are designed with regular geometric shapes. The trapezoid is the most common shape for channels with unlined earthen banks. Generally, it has stable side slopes. The rectangle. Channels having rectangular cross sections are built of stable materials such as lined masonry, rocks or timber. Triangular sections are used only for small ditches, roadside gutters and laboratory works. The circle is a popular cross-section for sewers and culverts. In practice, other shapes are also used, where the sharp corners are rounded off. These are parabolas, round-cornered rectangles, and round-bottom triangles. Now the question is, which is the most efficient cross-section? The efficient cross-section is the one which, for a given slope and area, has the maximum carrying capacity. For such a section, the wetted perimeter will be minimum and hydraulic radius will be maximum. For an open channel, the semicircle is the most efficient cross-section. However, if the rectangular cross-section is chosen, it will be half of a square, that is, the depth equal to half of the width, to make it the most efficient cross-section. If the cross-section chosen is triangular, the angle between the side slopes should be 90 degrees. But in practice, trapezoidal sections are mostly used to carry large discharges. Half of the hexagon is the efficient cross-section in this category. The channels are aligned so as to permit gravity irrigation in maximum possible areas. The alignment should be such that it reduces the capital investments and maintenance costs and saves the transmission losses. Let us understand the alignment of canals with the help of a model. Irrigation channels are generally aligned with reference to contours. A channel aligned nearly parallel to the contours of the country is called a contour channel. As some contours are higher on one side of the channel, a contour channel irrigates only the other side of the country. While laying a canal system, we may encounter natural drainage such as a river which crosses the canal at right angles. When the drainage bed level is lower than the canal bed level, we construct an aqueduct to carry canal water. An aqueduct is preferred when the drainage is wide and of higher discharge capacity, and the water flows for longer durations. But the situation may be reversed as well. When the bed level of the river is higher than the canal bed level, a super passage is constructed. It is a case when the canal is in deep cutting. However, when the headway clearance between the river bed and canal supply level is small, a canal siphon is built. The canal water is passed through an inverted siphon under the drainage, and the bed level of the canal is raised again on the other side. If the river and canal are almost at the same bed level and the flood discharge is intermittent and large, it would be economical to build a level crossing with regulating structures. In this system, sometimes the canal supply can be augmented with river discharge. After the head reach, a channel aligned along the ridge of a watershed is called a watershed channel. It can irrigate on both sides. Here, cross-drainage works are obviated. A channel aligned roughly at right angles to the contours is called a side slope channel. The cross-drainage works do not intercept this channel. However, in the alignment of the canal, there may be a situation that we may have to avoid religious places, other monuments and villages. In order to avoid these obstructions, to fulfill topographical conditions, and for diversion works, curves in the channels are introduced. Curves in unlined canals are made as gentle as possible, since they lead to disturbance of the flow, and they also have a tendency to silt on the inside and to square on the outside of the curve. For the same discharge, the radius of curvature for lined canals is less than for the unlined canals. Effectiveness of an irrigation channel network depends primarily on the command area it serves. Therefore, channels used for water distribution purposes require a high level at the point of delivery to serve the area under command without any difficulty. Normally, the channels with high discharge require less slopes than smaller ones. When the fields are high, adjacent to channels, water may have to be lifted from the channel. The side slopes of the canal depend upon the nature of the soil in which the channel is to be excavated depth of cutting, and the height of the embankment. Generally speaking, side slopes should be made as steep as possible and should be designed for high hydraulic efficiency and stability. The minimum slopes usually allowed vary from 1.5:1 to 2:1 for cutting. For loose sand embankments, the side slope ratio varies from 2:1 to 3:1. When canals are dug through rocks, the slopes are kept maximum, varying from 0.25:1 to 0.5:1. In order to allow for fluctuations in water level, a freeboard is provided. The freeboard is measured from full supply level to the top of the bank. The amount of water that we feed in a channel does not reach the fields. A major portion of the water is lost through seepage. The seepage losses constitute 35 to 50% of available water at the canal head. Seepage losses are considerably reduced by lining the canal. Lining also prevents water logging, weed growth, and reduces silting and erosion in the canal. Various types of lining can be mainly grouped into two categories: exposed and hard surface linings, buried membrane linings. The initial cost of exposed linings is generally high. They are recommended for use where structural safety is the primary consideration. There are several types of linings. Thick compacted earth lining may prove to be economical where suitable material for construction is available at site. Boulder lining is another economical lining where boulders obtained during excavation are readily available. It has very little flexural resistance or flexibility. Such lining is not satisfactory for canal infilling. Brick lining has been extensively used. It has the advantage of low initial and maintenance costs and quicker construction. Cement concrete lining is preferable because of its greater resistance to erosion and where the channel is to carry high velocity water. Precast concrete tiles are more compact and impervious. These tiles are laid in 1:3 cement mortar in single or double layers directly on the compact subgrade. In shotcrete lining, cement mortar is applied by pneumatic pressure. It can be placed over rough subgrade. Sandstone lining is used in field channels depending upon its availability and cost effectiveness. Plastic film and a layer of bentonite protected by earth or gravel cover are cheap linings. These are commonly recommended linings. But the drawback in membrane linings is that it is susceptible to damage by weed roots. In this case, permissible water velocity is also limited in order to avoid erosion. Out of so many types of linings, what are the criterion used in the selection of a lining? We put this question with reference to the modernization of the Upper Ganga Canal to Shri R.C. Goel, Chief Engineer, Irrigation Department.
The basic criteria are two. costs and the time that we use in their construction. As I said, concrete lining is definitely faster to do when we do it in bed. And cost-wise, concrete lining in the bed is a little cheaper also. But if we were to do concrete lining on the slopes, though the materials cost would be comparable, but the labor cost would increase because it needs shuttering and all that. Initially, we started with concrete lining because we had the experience of it and it could be readily started. Then later on, we established a factory for concrete tiles. Side by side, we started a new kiln factory to build up clay tiles. In fact, in this area, ample aggregates sand is available in River Ganga, but concrete tiles are not that impervious as the clay tiles. Clay tiles are definitely far better in respect of abrasion and imperviousness. So now we are doing concrete lining in the bed, and most of the slopes we are having double tile, clay tile lining. By making a new lined canal, we are saving very substantial quantities of water to the tune of 240 million cubic meters, which will result in very substantial increases of agriculture production.
Now, the water is to reach the fields. For this purpose, we have a canal irrigation network. A canal which takes off directly from the headworks is called the main canal. Normally, no irrigation is carried out from a main canal. A canal taking off from the main canal is called a branch canal. Distributary channels are taken off from the branch canal and sometimes from the main canal. A distributary can be a major or a minor, depending on the discharge. Water courses are small channels, generally constructed by cultivators themselves. They run from outlets provided in the distributary channel and convey water to field channels. For water distribution, it is necessary to adjust the discharge in a channel to any known value. This adjustment is carried out by the regulator at the headworks. In this process, sometimes it becomes necessary to run a group of channels at a time and to keep remaining channels closed. This process of rotation is known as rostering, and the whole process of distribution of water to branches and minors is termed as canal regulation. In spite of regulation, the irrigation channels do not always draw their desired discharges because of silt deposition, which make the channel shallow. Therefore, the success of an irrigation project also depends on control of silt and weed roots. In a canal, silt is removed through a silt ejector which is constructed in the head reach of the canal, a little downstream from the offtake. The silt-laden water is led through the tunnels and flushed out through gates into a different channel. The silt excluder is another device which excludes the silt before it enters in the canal. Silt excluders are constructed at the headworks and are similar to the silt ejector. The silt-laden water is led through the tunnels and flushed out through gates into a different channel or into the same river. In this program, you have seen how much effort has gone into providing water in the canal systems so that more water can be made available. This water is precious, so we must make the best use of it.